Hello and welcome to another exciting mathematics video. In this one, we're going to look in the Calc book, Chapter 4, Section 1, Antiderivatives and Indefinite Integration. For a long time now, we have been learning how to derive, so we are going to now reverse the process, antiderive. Bullet points for the section: write the general solution of a differential equation and use indefinite integral notation for antideriving. Use basic integration rules to find antiderivatives. We're just going to think backwards. And then we'll be able to find a particular solution to a differential equation. And let me do this. On the left here, let's talk about deriving. For some reason, I always thought of deriving as a downward process. So I'm going to do a downward arrow there. Derive and down begin with the letter D. And let's think about the steps and the order we did them. First, we multiplied by the old exponent, So we brought our exponent down, we multiplied by that old exponent, and then step 2, we lowered exponent by 1. Lower the exponent by 1. Now, if we are going to antiderive, we are going to do the opposite operation in the reverse order. So in the other process, we lowered the exponent by, we multiplied by the old exponent. So now we're going to do the reverse of that. Instead of multiplying by the old, let's do it in reverse order. Here we lowered the exponent by 1. So our first step in antideriving will be to raise the exponent by 1. Raise exponent by 1. So we reversed the second step. Now we need to reverse the first step here. Instead of multiplying by the old exponent, we are going to divide by the new exponent. Divide by new. So 2 steps: raise the exponent by 1, divide the term by that new exponent. Whoop. And the book says here, to find a function, notice here it's capital F, to find a function capital F whose derivative is 3x squared, you might use your knowledge of derivatives to conclude that would be x to the third, because if we derive x to the third, we would get 3x to the second. So that function capital F is an antiderivative of function f. And that's in our definition box here. A function capital F is an antiderivative of f on the interval I when capital F prime. Now notice all this notation. Capital F that is derived. So we're using the capital F to denote an antiderivative. So here, this is an antiderivative that we are deriving. So those are going to cancel each other out, and that's just going to be f of x for all x's in that interval. And I still have my name selector open, so I'm going to close that. There we go. So raise the exponent by 1, divide by the new exponent, and that's pretty small. Let me make this bigger so I can read it. Note that capital F is called an antiderivative of f rather than the antiderivative. To see why, observe that, here's x cubed. If we derive that, we get 3x squared. What about x cubed minus 5? Well, that's going to derive to 3x squared. The 5 derives away. What about x cubed plus 97? It's also going to derive to 3x squared. So all of these have the same derivative of 3x squared. In fact, for any constant c, the function x cubed plus c is an antiderivative of that function. And that leads us here to our theorem 4.1. If capital F is an antiderivative of f on the interval I, then g is an antiderivative of f on the interval I if and only if g is in the form of g of x equals f of x plus c for all x's in interval I where c is a constant. Does that make perfect sense. The way they word this, it can be kind of confusing, but if you slow down and read through it, it does make a lot more sense. It says here, if f is an antiderivative. So what they're saying here is we can take this and add or subtract any constant, and the derivative is still going to be the same, because this constant's going to derive away. So these will derive to the same thing. And then what's this down here? Oh, yeah, I still got to read that. Using this theorem, we can represent an entire family of antiderivatives of a function by adding a constant to a known antiderivative. So here it says if we derive x squared, we get 2x. And we can represent the family of all antiderivatives of this by simply adding a plus c at the end. So it would be g of x equals x squared plus c. C is just some unknown and arbitrary constant. That constant c is called the constant of integration. The family of functions represented by capital G is the general antiderivative of f. And g of x equals x squared plus c is the general solution to our differential equation, g prime x equals 2x. A differential equation in x and y is an equation that involves x's and y's and the derivatives of y. Something like this, y prime, our derivative is equal to 2x, or y prime, our derivative equals x squared plus 1, are examples of differential equations. So here we go. Example 1, find the general solution of this differential equation. Y prime is equal to 2. So I'm going to write it like this instead of y prime. In my class, you know I love the Leibniz notation. So that's dy dx equals 2. We can multiply both sides by the dx. So dy equals 2 dx. Now, we're about to find the derivative of this. Oops, I don't know if you heard that. Somebody come to the door while I was recording. So let's see here. We got dy equals 2 dx. Now we're going to antiderive each side. What is the antiderivative of dy? Well, that would just be y, because what do we get when we derive y? dy. Now here, just to keep up with our rules, we could put in here, it's not going to hurt anything, an x to the 0 power. Because remember, we want to raise the exponent by 1 and divide by the new exponent. So if we just see a constant, you can always assume there's an x to the 0 there. And now to do the antiderivative steps, we're going to take 2x, we're going to raise the power by 1, and we're going to divide by the new power. And then we are also going to add on our constant of integration. So there's going to be a plus c. So here, our general solution is y equals 2x plus c. And there we go. Because if we derived this, the derivative of y would be dy dx. And what's the derivative of 2x? It would be a 2. And our constant would derive away. And there we go. Ooh. Now here, when they talk about a family of functions, here's what we could see graphically. Y equals 2x. If it's 2x plus 0, that would be this blue line I'm drawing over. This would be 2x minus 1, because it goes through negative 1 on the y-axis. The green one would be 2x plus 2. If you derive any of these, 2x plus or minus any constant, the constant will derive away, and the derivative of 2x is 2. What's next? More reading. The operation of finding all solutions of this equation is called antidifferentiation, or indefinite integration. It's denoted by this integral sign. Sometimes in class I'll just call it the squiggly. It's kind of an elongated S. So the general solution is denoted by y equals, we have our antiderivative symbol, Our integrand is this function that we are going to antiderive, and the dx is going to tell us our variable of integration. If it's a dx, we'll integrate with respect to x. If it's a dy, we would do it with respect to y. When we do the process, the antiderivative of the lowercase f of x is denoted with a capital F of x, and then we tack on our plus c, our constant of integration. So down here, the expression, the antiderivative f of x, is read as the antiderivative of f, our function f, with respect to x. That dx tells us our variable of integration. So the differential dx serves to identify x as our variable. The term indefinite integral is a synonym for antiderivative. Antiderive, indefinite integral, same thing. So let's talk about some basic integration rules. The inverse nature of integration and differentiation can be verified by substituting capital F prime of x for f of x in the indefinite integration definition to obtain. And here's a quick refresher. Remember squares and square roots. If I have x squared and the square root of x, they are inverses of each other. So if I take this x squared and I square root it, the square and the square root cancel, and your answer is x. Same thing here. If I start with the root of x and square that root, out pops the x. So squares and square roots are inverse operations, and so are antideriving and deriving. So here, pay special attention to the notation. Here in the first one, this is the antiderivative, and this is a derivative, capital F prime. So in this case, the indefinite integral sign and the prime are going to cancel each other out, just like squares and square roots. So we see here that is equal to just capital F of x, and then we add on our constant of integration, because we're antideriving something. Now, if we reverse the order, here is an antiderivative of f of x, and then once we have that, we're going to derive that answer. So again, just like squares and square roots, we are deriving an antiderivative. So those are going to cancel out, leaving just the f of x. Notice in this case there is no plus c. If I go back up to here, our outer operation is antideriving. So at the end, we're going to antiderive something. When we do, a plus c will get attached. If we do that process down here, our inner operation is antideriving. So when we antiderive here within the red brackets, a plus c would appear, but then we are going to derive that answer. So when we derive it, we are going to get back to f of x, but the plus c will derive away because it's just a constant. So again, just like squares and square roots cancel, antiderivatives and derivatives will cancel each other out. And then these two equations allow us to obtain integration formulas directly from differentiation formulas. You know, all the stuff we learned deriving in the first half of the class, if we just think backwards, we'll get the antideriving. So here on the left are the rules for deriving, or excuse me, differentiation formulas on the left, integration on the right. So let's look here. Remember when we learned derives, we would bring down the old exponent and lower the exponent by 1. Here is the inverse of that. We're going to take the exponent and add 1 to it, n plus 1, and divide by the new exponent. And then let's think of our transcendentals. The derivative of sine is cos, so that means the antiderivative of cos will take us back to sine, plus c. The derivative of tan is secant squared, so the antiderivative of secant squared is tan x plus c. So all the rules we've learned, you just got to think backwards. E to the x is an easy one. The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x plus c. And that's good enough for the video, I guess. So again, everything we learned to derive, we will just back up to get our antiderivatives. Okay, here we go. Example 2. Antiderive 3x to the first power. So we are going to raise the power by 1, 3x to the second power, and divide by the new power. Don't forget to put on your plus c. And of course, you could also write that as 3 halves with the x squared off of it plus c, or the x squared could be in the numerator with the 3, as long as it's not distinctly in the denominator. Now what's this? When finding indefinite integrals, a strict application of the basic rules tends to produce complicated constants of integration. See, now here, this is a different way we could have looked at this one. You know, if we wanted to do step by step, the first thing we could have do is taken the 3 out in front of the integral sign. And then we antiderive and get x squared over 2 plus c. And then we distribute the 3 and you get 3 times c. But remember, c is an unknown and arbitrary constant. 3 times some unknown constant is just another constant. So we could just leave that 3c as c, because again, we don't know what c is. What's this? In example 2, note that the general pattern of integration is similar to that of deriving. We have our original integral. We will rewrite it. We will integrate or antiderive it, and then simplify, much like we did with deriving. And you're going to see that even more here in example 3. Okay, each of these are separate. So here's our original integral, antiderive 1 over x cubed dx. We're going to rewrite it as x to the negative 3 dx. And now we're ready to apply our new rule. We are going to raise the power by 1 up to the negative 2, and we will divide by that new exponent negative 2, and we're not going to forget to add our constant of integration. Now, don't leave your answer like this. Negative exponents are bad manners. So I'm going to switch ink colors here. We do have a plus c at the end. Let's see, the negative 2 is going to stay downstairs. But the x to the negative 2 is going to go down there and join it, where it becomes x to the positive 2. And that's going to leave a placeholder 1 in the numerator. So there we go, negative 1 over 2x squared plus our constant c. Letter B. The antiderivative of root x, or that would be the antiderivative of x to the half dx. So when we antiderive, we are going to raise the power by 1 to the 3 halves and divide by that new exponent 3 halves plus c. Now I've ran out of room to put the simplification, but I'm just going to work it here. Remember, we're going to bring this denominator fraction up and flip it. Multiply by the reciprocal, so this is going to be 2/3 x to the 3 halves plus c. There's our antiderivative. And remember, if we want to check our work, if we derive this, we should get back to where we started. So if we want to derive this, we're going to bring our exponent down and multiply it by what's in front. So that's going to be 2/3 times 3 halves. That'll be 1 over 1, or just 1, x. And we would lower the exponent by 1. 3 halves minus 2 halves is 1/2. The constant would derive away, and we're back to where we started. Up next, a transcendental. So we want to antiderive 2 sine x dx. We got to remember, well, I guess for the rewrite, the most we could do is pull the 2 out. 2 antiderive, that's a terrible s, sine x dx. So we'd ask ourselves, okay, what do you derive to get sine? Well, that would be negative cos. So we're going to have a negative cos x, and we're going to put the 2 back in and put on a plus c. Negative 2 cos x plus our constant. Okay, now this one, if you just go into it blindly, don't write this in your notes. If we do bring that up, that would be 3x to the negative 1. Say, okay, now we're ready to raise the power by 1, 3x to the 0, and divide by the new power. We cannot divide by 0. This is not going to work. And if we think back to our deriving rules, what did we derive? Let's move the 3 out. 3 antiderivative 1 over x dx. Do you remember what we derived to get 1 over x? Well, that was our natural log. So this, which I'm going to block off in black ink, the antiderivative of 1 over x, that is going to turn into the natural log of the absolute value of the denominator. 3 natural log of the absolute of x plus c. Now for the simplify part, we could leave it alone. That's a good answer. But we could also move that 3 up. Remember, this is just a misplaced exponent. We could move that up here so that the same thing would be the ln of x cubed. And because it's cubed, the bars would still be necessary. Plus c. So there is our antiderivative. If we derive this, we should get back to where we started. The ln of x cubed, remember that would be u prime over u, so our u is x cubed. Derivative would go on top, 3x squared, and we could reduce these down and knock that down to first power. We're back to 3 over x. Oh, and of course the constant would derive away. Up next, example 4, integrating polynomial functions. All right, now the first one here is probably the most confusing. I don't see anything after the antiderivative sign and the dx, but you know there's an implied 1 in there. And how about an x to the 0 dx? Okay, now it looks a little different, but it's easier to apply our new anti-deriving rule. We're going to raise the power by 1, x to the first, divide by the new power 1, and add on our constant of integration. So that's just x plus c. What do you get if you derive x plus c? The x would derive to a 1, the c would derive away, and that's what we have right here. It worked. Now on this, I see every year it is very easy for students to say, okay, well, here's an exponent 1. I'm going to raise the power by 1 and divide by the new power. In this case, it would actually work because this is a 1x in here, but anything else, it's going to be wrong every time. What we want to do is just antiderive this in pieces. What is the antiderivative of x to the first? That's going to be x squared over 2 plus. What's the antiderivative of 2x to the 0? That's going to be 2x to the first divided by 1. Don't forget your constant of integration. And I personally would write this as 1/2 x squared plus 2x plus c. I just don't like to have my variables on top like that. I like them to slide off. It's a little more at least pleasing to my eye. But there is my final answer. Last one here. Now this is one if we put a first power out here and then just tried to raise the whole quantity and then divide by 2, that's going to be wrong because we have more than just x's in here. So this definitely we want to take on a piece-by-piece basis. So let's antiderive the first term. 3x to the 5 over 5. Raise the power by 1, divide by the new power. Next term, 5x squared is going to become 5x to the third over 3. X to the first is going to become an x squared over 2. And don't forget that constant of integration. There's our final answer. Raise that power by 1, divide by the new power. Example 5. Very similar to ones we did when we were deriving. At the point, we did not have a rule to derive a quotient. We didn't learn the quotient rule yet. So what we did, remember, we would give each of the numerator pieces their own denominator. Our denominator is just a root x or x to the half. So what we can do is break this up. We have an x and a plus 1. Let's give them each their own x to the half denominator. X to the half, x to the half. Put my dx on there. Okay, so now we've broken it into 2 more bite-sized chunks. Let's simplify each chunk and get it ready to derive. So here's x to the first over x to the half. Subtract exponents. 1 minus a half is a half. Plus, let's rewrite this as x to the negative half. Dx. And now everything is ready to antiderive. So, first one, x to the half. Let's raise the power by 1 to 3 halves and divide by the new power 3 halves. Here we're at negative a half, so when we add 1 to that, it will become positive a half, and we will divide by that new exponent half. Don't forget your constant of integration. Many tears have been shed over forgetting that constant. So now this is a good answer, but it's not aesthetically pleasing. Fractions within fractions is just horrible. So let's bring this up and flip it. 2/3 x to the 3 halves plus, bring this up and flip it, 2 x to the 1 half plus our constant. There we go. There's our antiderivative. If you don't believe me, just derive it, and you'd have to do a little work to get it back into this form, but it's doable. Okay, what's next? Holy cow, what the heck are we going to do with this? It's kind of all stuck together. My advice for any type of problem like this, especially involving trig functions, I see this cos squared. It might be helpful to break that up. There we go. So this cos squared is a cos x times a cos x. Now I've only got a sign in the numerator. I can put it over one or the other, and it really doesn't matter because they're both the same. So that's a sine x, and we'll put a placeholder 1 there. Okay, think back to pre-calc. What is sine over cos? Sine divided by cos is tan. So that's a tan x times 1 over cos. Well, that's secant x. All right. So now remember, we need to think backwards. There was something that we derived, d dx of something was equal to secant x tan x. Think back to the little trick I showed you to remember derivatives, SST. So the derivative of secant was secant times tan. So then that makes sense. The antiderivative of secant times tan, like we have here, is going to take us back to secant of x. So this antiderivative is just equal to secant of x plus c. Because, of course, again, we could check our work by deriving. If I derive this, I should get back to where I started. What is the derivative of secant of x? Well, that would be secant times tan. Secant x times tan x, and the constant would derive away. So we got it again. Good job. What's next? Oh, another one of those rewrite and then anti-derive. Okay. Oops. So here we go. We've got in the denominator root x, or that'd be x to the half. Let's bring it up and make it 2x to the negative half. So we did a rewrite to get it in the proper form. We can now integrate using our rules. We're going to have 2x, and we're going to raise the power by 1. Now we're up to positive a half. We will divide by the new exponent, positive a half, and put on our plus c. Now let's bring this denominator fraction up, flip, and multiply. So that's going to become a 4x to the half plus c. That's a terrible denominator there, but you get the idea. 4x to the half plus c. If we derive that, it should get us back to where we started. Now this one, there is a way we will learn eventually to antiderive a quantity squared, but for now, let's just FOIL it out. So this is I'm going to write it up here because I'm going to sort of run out of room. If we FOIL that out, t squared plus 1, we're going to have t to the 4th plus 2t squared plus 1. So that is our rewrite. We've just rewritten it, expanding it out as a binomial. Now let's antiderive each term. First term, t to the 4th, we raise the power by 1, divide by the new power. Next term, 2t squared, we raise it to 3rd and divide by 3. The last one here, this would be 1t to the 0. So we're going to raise that to t to the 1st divided by 1, or just t. Don't forget the constant of integration, plus c. Letter C is a lot like the last example. We are going to break it into two pieces. Numerator x cubed over x squared. So x cubed over x squared is just x, plus, then we would have a 3 over x squared, which is 3x to the negative 2 dx. So there is our rewrite. Now I'm going to sneak down here for the antiderivative. That's x to the first. So we are going to raise the power by 1 and divide by the new power. Plus 3x to the negative 2, we will raise that to the negative 1 and divide by the new exponent negative 1. And don't forget your constant of integration. So now just to make this look a little prettier, we just got to get rid of that negative exponent. And again, this is just my personal preference. I'm going to make this a 1/2 x squared. Now this plus is going to be overpowered by this minus, so now it's going to be a minus. And the x to the negative 1 is going to move downstairs. Be careful, the 3 has its own exponent. That 3 is going to stay in the numerator. X to the negative 1 goes downstairs, so now it's just an x down there. And our plus c. And there's our antiderivative. The last one we're going to have to distribute before we can antiderive. So out here, this would be x to the 1/3. Here's the rewrite. X to the 1/3 times x to the 1. So we add the exponents. 3/3 plus 1/3 is 4/3. So x to the 4, that's a terrible 3, x to the 4/3. And then minus, we will distribute x to the 1/3 to the 4. So that'll be 4x to the 1/3 dx. So there's our rewrite. We are now ready to antiderive, and I'm just going to move some of this stuff up here a little bit, like this. So first term, x to the 4/3, we're going to add 1. 4/3 plus 3/3 is 7/3. We will divide by the new exponent 7/3 minus 4x 1/3 plus 3/3 is 4/3. 4/3. Divide by 4/3. Don't forget your plus c. There's our constant of integration. And now I guess I'll just work my way back up here, and I'll switch over to blue ink for the final fix up. So here we're going to bring up this denominator fraction and flip it. So that's going to be 3/7 x to the 7/3 minus 4/3 is going to jump up here and become 3/4 and multiply by the 4 that's already there. That will be a 3 x to the 4/3, and then plus our constant. And that's our final answer. Nice. So again, this plus c, that's just some constant. If we derive, it's going to derive away. Oops. Now, we talked earlier, we were finding general solutions. A general solution has a plus c. Particular solutions, we solve for c. Like over here, we've got a family of functions, x cubed minus x plus c. If we graph that, we're going to have these curves. For different constants, we'll have different y-intercepts. So here, are all our different functions. If our constant is 4, we would use this top one. If our constant is 3, it would be this one. So in the setup to these problems, you will find the general solution, the antiderivative with the plus c, and then they're going to give you a point. That point we will use to solve for the specific c that we're looking for. And let's read some of this here. Okay, so initial conditions and particular solutions. You've already seen that the equation y equals the antiderivative of f of x dx has many solutions, each different from the others by a single constant. This means that the graphs of any two antiderivatives of f are just vertical translations of each other. And it says, for example, in the figure, it shows the antiderivatives of this. Whoops, I already showed that to you. Blah, 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 blah. For various integers values of c. Each of these antiderivatives is a solution to this differential equation. dy dx equals 3x squared minus 1. Because if we derive x cubed minus x, we would get 3x squared minus 1. In many applications of integration, you're given enough info to determine a particular solution. To do this, you need only know the value of the function for one point. This information is called your initial condition. For example, in figure 4.2, only one of the curves passes through the point 2, 4. So here on the picture, there's the point 2, 4. That only is hit by one of those curves. Oops. So to find this curve, we use the general solution, f of x equals x cubed minus x plus c. And this initial condition, f of 2 is equal to 4, means we put 2's in for all the x's, and we set the whole thing equal to 4. So now the only thing left unknown is c. So we go through and solve for c, so we can write our particular solution. Notice here the general solution has a plus c on the end. The particular solution, the c has now been replaced for the specific c value that we've been looking for. General solution plus c, particular, you solve for that c. And here's example 8. Let me make this a little bit bigger. There we go. Find the general solution of f of x equals, or f prime of x equals e to the x, and then find the particular solution that satisfies this initial condition. Now here's one way they give it to you. They say that f of 0 equals 3. This is also the point 0, 3 is on the graph. Our input x is 0, our output is 3, so that is a point on the graph. So I'm just going to copy this down here. Capital F prime of x is e to the x, and we've got our point 0, 3. So now here on this side, if I antiderive, the antiderivative and this prime notation are going to cancel. So that's just capital F of x equals, what is the antiderivative of e to the x? Well, that's e to the x plus c. Again, just for clarity, this is the general solution. We've antiderived. It has a plus c on the end of it. Let me get this up here so I have a little more room to work. So there's our general. Now we are going to use 0, 3 to solve for c. So capital F of 0 would be e to the 0 plus c, and we set everything equal to the y value, 3. So what is e to the 0? Well, anything to the 0 is 1. 1 plus c is equal to 3. C then would be equal to 2. So I'm going to erase this stuff in here. There we go. So our general solution, e to the x plus c. Our particular solution is f of x equals e to the x plus 2. This is the particular solution. The c has been solved for. And we can look at that here in the graph. Again, each of these in the family is only different by a constant. So we've got all these lighter graphs here. The only one that goes through our point, 0, 3, is this one. So our constant of integration would be a 2, e to the x plus 2. And I think that just leaves one more example. Yes. This, remember way back when we learned deriving and initial velocities and all that stuff, we had a diver diving into a pool. Here, we're going to do a similar problem, but in reverse. So it says in the book, so far in this section, you've been using x as the variable of integration. In applications, it's often convenient to use a different variable. For instance, in the next example involving time, the variable of integration will be t. So, solving a vertical motion problem, and I'm going to start a new slide here so I can put this on that. I don't want to have it too small when we're working on it. Get over there. We go. All right. A ball is thrown upward with an initial velocity of 64 feet from an initial height of 80 feet. Find the position function given the height s as a function of time t. When does the ball hit the ground? So, for part A, let t equal 0 equal initial time. INITIAL, initial time. Oop, that is just a terrible M. There we go. So we have our initial time. S of 0 is going to be our initial height. So before the problem starts, how high is the ball above the ground? Well, we're at an initial height of 80. So S of 0 equals 80. We have initial velocity is 64. So now remember when we were doing this before, velocity at time 0 is going to equal 64. That's our initial velocity. And remember that velocity was the first derivative of position. So S prime is equal to V. V of O is equal to 64. And they don't give us in this problem, but we can't get started without it. Remember, the second derivative of position is equal to the derivative velocity, or that is our acceleration function, a of t. And remember, here on planet Earth, that is negative 32 feet per second squared, feet per second per second. That's not secant squared, that is our time units seconds. So these are our initial conditions. And I'm going to have to start a new slide because I don't want to erase these. We are going to need these as we solve for constants. S of 0 is 80. V of 0 is 64. A of 0, negative 32. So these are initial conditions that I'm going to have to refer back to as we work our way through this problem. So again, I'm going to start a new slide. And we got to begin somewhere. We're going to start way down at the second derivative, and we're going to anti-derive our way up to position. So S double prime of t on planet Earth, that is our gravitational constant, negative 32. Let's anti-derive. If I anti-derive S double prime, that's going to take us up to S single prime, one layer up. What is the antiderivative of negative 32? That will be negative 32t plus c. We'll call it c sub 1. That's the first constant we have encountered. So we're going to use one of our initial condition. Use initial period condition here. So we're going to use, if I back up, the S prime. And that is our 0.64. So here's our S prime at 0, first derivative S prime. So we're going to put a 0 in for all the t's, and we're going to set it equal to 64. So S prime of 0, we put zeros in for t, plus c sub 1, and we set it equal to 64. Now, of course, the negative 32 times 0 is 0, so c sub 1 is equal to 64. So I'm going to erase this and replace this c sub 1 with a 64. So S prime t is equal to negative 32t plus 64. We've anti-derived our way up one level. From s double prime to s prime, we got the constant out of the way. So we want to anti-derive again. Remember, we want to get to s of t, and we're one layer down, we're one derivative down. So we are going to anti-derive again. The antiderivative of s prime is going to take us to s of t, our position function. Now here, the first term, negative 32t, we are going to raise the power of t by 1 and divide by the new power, plus 64 t to the 0 is going to become 64 t to the first. And then we get our second constant pop up, c sub 2. So we've encountered another constant for s of t. We have an initial condition to take care of it. If I back up here, my initial condition for s is 0, 80. So we're going to put in zeros for all the t's, and we're going to set the whole thing equal to 80. So that's going to be a negative 32, 0 squared over 2, plus 64 times 0, plus c sub 2, and we set this equal to 80. So this here is going to be negative 16t squared. I should have done that. You know, we could simplify that to a negative 16, but it doesn't matter. It's going to get all wiped out, and our c sub 2 is equal to 80. So again, I'm going to erase this down here, and I'm going to replace this c sub 2 with the 80 that we just found. So s of t is equal to, let's simplify that to the negative 16 t squared plus 64 t plus 80. And that's our final answer for part A. Part A said find the position function for the given height and time. This is our position function, s of t equals that stuff. Oops, get back, there we go. Now what was part B? When does the ball hit the ground? So what do we want to do with that? We want to set position equal to 0. So there will be no calc involved in this. We've just done a bunch of calc to get here. So when does the ball hit the ground? When position is equal to 0. So I'm just going to move this over here and set it equal to 0. Now we are going to have to factor this. The good thing is we can factor out a negative 16. And then we're going to have t squared minus 4 minus, that's 4t, minus 5 equal to 0. So what is in those parentheses factors down. A t minus 5 and a t plus 1, and that's equal to 0. We can divide the negative 16 out and then set each of these to 0. So we're going to get t equals 5 and t equals negative 1. Now remember, do these make sense? Our question was, when does the ball hit the ground? Does it hit the ground negative 1 seconds after we throw it? No. No time travel here. That is a nonsensical answer. Here is our answer. T is 5 seconds to impact. 5 seconds to impact. All right, that was a good one, and we really didn't even need the graph, did we? I guess we could have put our points on there. You know, 0, 80, we would be here. At 5, we're back at 0, so we would be back on the x-axis, and we could just, you know, figure out some y values for when we put these t values in there. Again, not overly critical, I guess, to the understanding of this problem. But we could put some in there. Let's do a 1, 128. So if we're at 1, we're just going to be below 130. So right there, there we go. At 2, we're up here at 144. 2, 144. That looks like our peak. Because at 3, we're back at 128. And then at 4, we're at 80. 4, 80. So, we're standing on the edge of a cliff. We throw something up in the air. It reaches its peak. It's coming back down. Here it's back to the height of the cliff, but it's got to fall an extra 80 feet to get back to the ground. That's going to take 5 seconds. All right, good stuff. That is the end of this section's examples. Next time we're together, we're going to do some odd problems and some worksheets that I have printed out. I will see you then.